So the goal is to find the non-trivial fixed point of this dynamical equation, which is determined by the condition that R1 minus n over k is equal to n1 plus n squared. I mean, this is in general a cubic equation, and so the solution to it is kind of messy. So once again, geometric tools are much more useful to get a basic understanding of the system. And so let's plot the left-hand side and the right-hand side of the equation of the function of n, and where they intersect will give us the fixed points. And as we'll see, this really helps determine the behavior of the system. So let's plot as a function of n, the left-hand side of the equation and the right-hand side of the equation. So the right-hand side is a function which starts off linearly with n, and then it decays like 1 over n. So let me draw it first. So it's some function that looks like this. So that's the right-hand side. Now for the left-hand side, let's, for the sake of simplicity, treat R as our control parameter. So we're imagining that there's a fixed carrying capacity in the forest. There's a fixed density of trees that produces a fixed number of leaves, and the only control parameter will be the reproduction rate of the spruce budworm. So we can imagine that in the wintertime they reproduce almost not at all, but when springtime comes they start reproducing like mad. And so we can ask what happens as R changes. So first point is that the left-hand side of the equation, when n is equal to k, it's equal to 0. Let's try and now look at the left-hand side of the equation for various values of R. So when R is very small, we might have something that looks like this for the left-hand side. And we see that there is a fixed point at a small value of n. However, if I increase R, then again it starts at the same point at n equals k, but now it just kisses the magenta curve. Now there is still a fixed point for small n, but a new fixed point is born at a relatively large value of n. As we increase still further, so as R increases still further, we have something which looks like this, for example, and we have a fixed point at a relatively small value of n, a fixed point at a large value of n, and another intermediate fixed point. And finally, when we increase R still further, we reach a situation where there is only a single fixed point at a relatively large value of n. So where we have a large value of the number or the density or the number of spruce bedworms, this is what might be called the outbreak. And in the field, the region where there's not very many spruce budworm, this is called the refuge state. And to finally illustrate what's happening, let's look at the equation of motion itself, n dot as a function of n. Roughly speaking, what's happening is that in the case where R was very small, we have something that looks like this. So this purple curve is supposed to correspond to the purple line on the figure on the left, and there's a fixed point value here. As we increase R, so the function starts with a higher slope, and now this hump barely kisses the x-axis. And as we increase R still further, so corresponding to the orange curve, we have a situation where we have 3 fixed points. This is the stable fixed point, this is the unstable fixed point, this is the stable fixed point, and that's what we see in the orange curve intersecting the curve n1 plus n squared on the left. And as we increase R still further, we have something like this, where we no longer have other secondary fixed points, but there's only one fixed point at a large value n. So as our control parameter R increases, we go from one fixed point at a relatively large density of budworms to one fixed point with a small density of budworms, but in between there are multiple states that can exist, and this arises because of the multiple peaks and valleys of the curve of n dot as a function of n. So this is the basic phenomenology of the spruce budworm outbreak.